everyone! Today we will be doing the full reimplementation of the masked AutoEncoders pre-training, and then we'll briefly look at the supervised fine-tuning. The supervised fine-tuning, the code is identical. It's literally copy-pasted from my vision transformer code. So that's why I won't be going into too much detail there. I'll kind of just briefly go through it, and if you want more details, you can go watch that video and I'll link it down below. We're mostly going to be focused on the pre-training. The reason we can just use the vision transformer training code that I already wrote earlier is because the encoder, of course, of the masked autoencoder is just a vision transformer. We're just using it in a slightly different way. I did a quick paper overview. It's already posted. I'll put that link down below as well if you want to get some more details about the paper, but I'll make sure I reference those details as we go on. So just to get started, essentially just to warm up, like I said, this is essentially just a vision transformer. So we need to implement some parts of the vision transformer that we're going to use in the masked autoencoder. Of course, we need our patch embedding. So let's do this. So if name is main, the shape of the images we'll be working with will be rand is torch.randn 1x3 channel by 224 by 224. And so let's go ahead and implement our class patch embed. The nn.module, and this is the thing that's going to take our images and patchify them. And of course we could manually patchify them and then project them with a linear layer, but the more standard method is just to use non-overlapping convolution. So we're going to do it that way again. So image size is 224, our patch size is 16, normal 16 by 16 patches, in channels is 3, embed dim is 768, because we'll be implementing a base vision transformer, so in base masked autoencoder, so that's all the same, and whether or not we want a bias projection or not. So super.init. And essentially this is just a single convolution. So this is relatively straightforward. We're going to make sure that our image size is indeed divisible by our patch size, right? Which it should be. Because our image size is 224 divided by 16, that's 14, so that's fine. And then what we're going to do is just store a bunch of our information. Self.image size is image size. Self.patch size is patch size. Self.in channels is in channel. Self.embed dim is our embed dim, and self.num patches is equal to, well, how many patches do we have? We have a 224 by 224 image, and each patch, so let's go back to this figure, we have a 224 by 224 image, and each patch is 16 by 16, so we have a 14 by 14 block, basically a 1414 grid of our patches, and so it's going to be 196 in total, so that's pretty easy to calculate. It's just going to be the image size divided by our patch size squared, and that's it. And then our projection, the actual thing that's going to do this, is going to be nn.conv2d. We're going to go from in channels is in channels. Our out channels is going to be the embedding dim that we want. Our kernel size is going to be the patch size. Our stride will also be the patch size. So basically every kernel is going to look at a patch size by patch size location in our image. And then we're going to move over by patch size, so they're non-overlapping. So essentially we're going to take an image and perfectly cut it up into a grid with no overlapping patches. We could do overlapping patches if we want, but we don't need to in this case. So bias is bias. There we go. All right, so our forward, very simple. Def forward, self, pass an x is equal to self.proj. X, and let's just take a look. So we're going to do patch embed is our patch embed, and we're going to do pass in the rand, and so we can then print out x.shape, and you'll see pretty clearly that we have Python. There we go. So it's one batch by 768 by 14 by 14. So this is the channel dimension. These are the patch dimension. We mentioned it's a 14 by 14 grid. And each of those are represented by 768. So let's just go ahead and put it in the right shape. So we're going to do dot flatten 2 dot transpose 1 2. So all we're going to do is flatten these two dimensions to become 196 and then transpose those two dimensions. And now we'll get 1 by 196 by 768. So essentially to the transformer, we're passing in 196 positions, patches, and each patch is represented by a vector of length 768. And that's it, right? So that's our standard patch embedding. After that, we need our, basically the encoder itself. And the encoder block is a combination of a attention mechanism and our multi-layer perceptron. So let's just go ahead and write the standard attention mechanism, standard perceptron, and nothing else. So self attention encoder and then dot module. I already wrote all this code in the vision transformer, so you don't have to watch this. You can just skip ahead. I'll timestamp everything so you can skip ahead to where the actual masked autoencoder starts. But embed dim, I'm going to go ahead and just paste this in right here. And yeah, that's fine. And what we're going to do, I'm going to just keep pasting because I don't need to type any of this out. It's just storing some variables. So there we go. And there we go. So here we go and tab this forward. There we go. All right. So yeah, so this is our self-attention. How many heads do we have? If our embed dim is 768, then of course our head dim per head embedding is going to be 768 divided by 12. So we just verify that it's actually divisible. That's our head dim. And then we grab our scale in the, we have to divide by the square root of the head dim. So that's where we get that. And then we have whether or not we want to use fused attention or not, and we probably do, right, just for efficiency. Self.qkv is going to be equal to, I seem to be missing something. Class here, let's see. Oh, okay, maybe I'm just not tabbing it correctly. There we go. There we go. Okay, there you go. Yeah, something was off with the tabbing. Not really sure. So there we go. Okay, so self.qkv is going to be a linear layer and then .linear that's going to go from embed dim to embed dim times 3, because we're going to essentially just fuse the QKV projection into a single linear layer rather than having 3 separate Q that goes from embed dim to embed dim, K, embed dim to embed dim, V, embed dim to embed dim. Let's just put it all in one, and then we can just split it apart afterwards. So that's one. And then our self.attention P is going to be the attention P. Self.attention drop is going to be nn.dropout attention P. If not, and actually let's just leave that, it's fine, it doesn't really affect anything. And then self.proj is going to be equal to nn. It's a linear, so this will be the post attention linear layer. Again, it's going to go from embed dim to embed dim, and self.proj drop is going to be nn.dropout proj p. So yeah, if any of this seems confusing, I have a whole video talking about attention, so we can just reference that. I don't want to dig into too many holes here because I want to make sure we're talking about the actual paper and not stuff that I already expect that you know going into this. So we have batch size, sequence len, embed dim is x.shape, so that's the data that's going to come in. And so qkv is going to be equal to self.qkv. We're going to pass an x, and we're going to reshape it. So this is going to project it to, it'll be batch by sequence len by embed dim, and then this is going to make it batch by sequence len by embed dim times 3, because that's what I projected it to. So let's go ahead and reshape it. So it's going to be batch size by sequence len by 3 by self.numHeads, or let's keep it simple, let's do by embed dim. So this is me taking the embed dim times 3 dimension and splitting it up, because I know that there's going to be 3 different embed dims, but we know that each of these embedding dimensions are going to be split into however many heads that we have. So we have to do one more split on top of that. So this embed dim is now going to be self.numHeads. How many heads do we have? By self.headDim, the dimensionality of each one of those heads. And so then QKV is going to be equal to QKV.permute. Just move all the dimensions around. We want the 3 first, so we can split on that, so 3. And then we have our batch size, so 0. Then we have our, or actually, wait, let me get this right. It should be 0, 1, 2. Should be 2. There you go, 2. So it's going to be first this dimension, which is 0, 1, 2, so 2. And then we want the batch size. And then we want the number of heads. So 0, 1, 2, 3. And then we want the sequence length 1, and then we want the head dim, which is going to be 4. So basically our new shape is going to be this 3, which we'll split on by batch size, by number of heads, by sequence length, by head dim. And that's our standard shape. And so then very simply QKV is equal to QKV.unbind or chunk, whatever you want to use on that first dimension. And that's going to go ahead and split everything up for us. And so each of these QKVs are of course then going to be batch by sequence len, or sorry, batch by num heads by sequence len by head dim. And now we can go ahead and do our attention mechanism. So if self.fused attention, if we want fused, and there's really no reason not to want fused, let's go ahead and do it. It's going to be x is going to be f.scale.product attention, just flash attention, QKV. And our dropout p is self.attention p if self.training else 0, right? So otherwise don't do it. Else, if we're not using fused attention, then it's a standard attention mechanism. So it's going to be q at k dot transpose, flip the last two dimensions, -1 or -2, -1, doesn't really matter. Multiply it by the scale, because I've already done e to the, or head to the power negative, so it's already reciprocal, so it's going to be times self.scale. After we have that, we can do attention is attention.softmax axis is -1 along the last dimension, and then attention self.attention drop attention, and then x is going to be attention at v. And so both of these are equivalent, but of course this is fused and faster, and that's why we prefer it. Then x is going to be x.transpose. So remember, our data is going to come out in the shape of, so x is in the shape of batch by heads by sequence length by head dim. I need to put these two dimensions back together, so let's flip these two and then flatten. So it's going to be transpose 1, 2, and then dot reshape batch size by sequence len by embed dim. And then x is going to be self.proj x, so this will be our post attention projection, and then x is self.proj drop x, and then we can return x, and we're done. Okay, good. So that's our attention mechanism. Of course, we also have a feedforward layer, so class MLP, nn.module, def init, yep, self, in features, hidden features, out features, the activation function we want, which by default is going to be the GLU activation, so we'll do that. And then MLP, our dropout probability on the this projection layer. So it'll be super.init. Self.fc1 is going to be a linear layer, linear from in features to hidden features. And then self.fc2 is, again, another linear layer from hidden features back to in features. We have our activation function, so we call it nn dot, or I guess we already have it above, so we can just grab it from there, act layer, just like that. And we have our dropout. Let's get rid of that. Self.drop1, so let's put that right here. Self.drop1 is nn.dropout, mlpp, and then we will have a second dropout right here, dropout2, again, mlpp. And so then our forward method, very simple, def forward self x, and we're going to do self.x is self.fc1x. First we pass it through the first linear layer. X is self.activation function, go through the activation. X is self.drop1, and then x is going to be self.fc2, the second linear layer. X is self.drop2 x, the second dropout, and then we return x, and that's it. So that's our multi-layer perceptron. And so now we can very simply put all this together to make our encoder block, and the encoder block is just going to be this, and we just have all the stuff, you know, the arguments we need. This should be out features right here, my bad. So we have all the arguments we need. Technically, in standard attention mechanisms, the in feature should equal to the out feature, so it'd be correct either way, but still. And so these are all the stuff that we had. And so all we need to do is just put it together. So we're going to do super. Here, I'll just paste this part actually, because There's nothing here, it's just using the methods. So we have our first normalization, we're using layer norm. So we have normalization, we have our attention, we have another normalization, we have our multi-layer perceptron. So then in our forward method, def forward self x, x equals x plus, because residual correction, self.attention, self.norm 1, x. So these are pre-normalization. A lot of architectures today are using post-normalization. So after attention, they'll do it, but either way, it's fine. So x is then equal to x plus self.mlp, self.norm 2, x. And then we return x, and we are done. So let's give this a test. Our encoder block, so let's call it B, is the encoder block. And into B, we're going to pass in the output of the patch embedding applied on rand. So let's print out.shape. So let us check for any bugs. Oh, there you go, right? So everything is correct, and we're good to go. All right. So now that we have that, those are kind of the pieces of the vision transformer that we need. We can now actually go on to write our masked autoencoder. So to do the masked autoencoder, there's going to be a couple things that we need. I am going to copy all the imports in, and we're going to write some. So these are the original imports. These are the new imports. So everything's the same. It's just this file no longer exists. We already implemented all of that. And this we don't have yet. We're going to add that in next time. So I'm just commenting it out for now. What we haven't written is a couple of these methods here. So let's go write these utilities out, basically to create our sine cosine embeddings, our random masking strategy, which we'll kind of describe a little bit better closer to the paper once we do it, and then our Patchify method. So we're going to need all this. The only other thing we're going to need from here for now is going to be this. So this is going to be the definition of our masked autoencoder. Basically the input image size, patch size in channels, which is kind of our vision transformer stuff. We have our encoder config. So remember, the masked autoencoder has a encoder portion and the decoder portion, and the decoder portion is supposed to be smaller. Like it's supposed to be a lightweight decoder, and we see that here. So our encoder has a depth of 12 attention head, 768 embed dim, pretty standard transformer essentially. Our decoder has a smaller embedding dim, so 512, and it has less layers. In the implementation, they use more heads here. Not exactly sure why. I don't know how much it matters. I don't believe there was an ablation study on the number of heads. So either way, we're just going with it. So yeah, but overall, there's going to be much fewer parameters in this one compared to the encoder, and we'll look at the parameter count later when we get there. There's some other stuff in here. This has to do with the, so this we'll need today for num classes. This has to do with segmentation stuff, which we're not going to look at today, so ignore that. And then we have some other stuff in here, which we have the masking ratio, and then some other stuff. We'll look at all this later. Okay, so for now, let's go ahead and do this. So in the utils, we're going to write a couple of simple utilities. The first one has to be our sine cosine embeddings. We could have also used learned positional embeddings like the standard vision transformer, but they opted to use sine cosine, so we're going to stick to the paper as much as possible. Sine cos cosine embeddings. And this is going to take in num tokens, like the number of positions, the embedding dimension, and requires grad. By default will be false because these are not trainable parameters. You can make it trainable, but we don't really need it. So we know that our embeddings should be in the shape of, so encoding for now is going to be, we're going to initialize it as zeros. It should be in the shape of num tokens, basically the max sequence length, by the embed dim. And dtype is going to be torch.float. That should be our default shape of the encoding. And if you remember, let me just pull up the tension is all you need paper, just so we can reference the equation, but it's relatively straightforward. Should be right over here. So basically, we want to do 10,000, that's the base value, to the power 2i over the dimensionality of the model. And we want to place the sign of the position divided by that at every position in the 2i, so every even position along the embedding dim. So for every position along the even embedding values, we want to put them in there. In the same way, we want to do the same thing, but in the odd ones for the cosine. So basically every even one will have the sine of this value, and every odd position will have a cosine of the value. And we'll do this for every single position. So let's go ahead and see what that looks like. So first we have our position index is going to be equal to torch.arange from 0 to num tokens. And dtype is going to be equal to torch.float. And we're going to do dot reshape -1, 1. So this is going to make basically a tensor of size sequence len by 1. And let's also do if name equals main. We're going to do sign Cos Embeddings. We're going to do, let's do 10 embeddings and an embed, or let's do 5 embeddings and an embed dim of 3, or I don't know, 12. That's fine. Okay, so let's just see what this looks like. Print position index. This should basically be a column vector. Oh, wrong one. We need to run utils. There we go. So it's a column vector of all the positions 0 through 4. So there we go. And encoding is initialized, of course, as zeros, but we need to populate this. And the thing is basically for every single position, so position 0, position 1, position 2, every even position should be populated with the sign of that value, and every odd position should be populated with the cosine of that value. And that specific value, of course, depends on the position itself, right? So that's how we change the frequencies over position. And then we have the change of sine versus cosine, whether or not we're in an even or odd index along the embedding dimension. So this is relatively straightforward. Then all we need to do is embed dim skip index is going to be equal to torch.arange 0 to embed dim, and we're going to do step equals 2. And again, dtype is equal to torch.float because we want every other one. So embed dim skip index is just going to be exactly which thing, 0, 2, 4, 6, 8, 10. So for every even position. Okay. So now that we have that, let's go ahead and populate them. We're going to do encoding for all the time steps in the sequence, but for every even position, so it's 0, this basically says 0 to the end in steps of 2. The second one is going to be 1 to the end in steps of 2, and that will be the odd positions, of course. But let's do the even one first. So torch.sign. We're going to do position index divided by 10,000 to the power our embed dim skip index divided by embed dim. And we can see it's because we have a 2i in the numerator. So that's the skip index, right? It's basically every other one. So that's exactly what this is. It's going to be 2i divided by the embedding dimension itself. And we'll do exactly the same thing for the denominator, right? So it's going to be sine for the first one, and then every odd position, not denominator, every odd position is going to be the cosine, and that's it. So if we print out our encoding, we should essentially see all our stuff populated just like that. And just to make it import matplotlib.pyplot as plt, we can quickly do plt.imshow encoding dot just make it numpy so we can actually see it, and then plt dot show. There we go. Oh, it's probably less helpful. Let's add more positions. Let's do 196 by 768, right? That'll be the shape we're working with for the vision transformer. So we'll plot the same thing. And we get that, right? So these are our standard sine cosine embeddings where every odd position along each vector has the cosine of the frequency at that time step. And then every even one has the same thing, just the sine along the other, the sine of the same thing. This is a completely fine way to do it. Another way you can do it is instead of like interleaving them in this way, like every even one, every odd one, sometimes you just do like the first half is, one of them, and the second half of the embedding dim is the other one. It can go either way, it doesn't matter. So, but we're going to stick to the original paper for simplicity. So then encoding is equal to encoding.unsqueeze 0. We're basically adding a batch dimension in there. And then encoding equals nn.parameter. Encoding requires grad is requires grad. Return encoding. So is it trainable or not? Depends on that. And then it's a parameter, so it'll move around with our model. Good. That's step one. The next thing we need is our random masking strategy. So random masking. And this is going to take some x and some mask ratio, which is going to be 0.75 by default. So let's take a look at the paper. So remember, the masked autoencoder uses 75% masking strategy. So for all 196 patches, or however many there are coming in, we'll randomly select 75% of them to be masked out. And it's really as simple as that. So what we're going to do is we're going to assume that x is of the shape batch by num tokens, should be 196 by default, by embed dim. And so for the positions that are, let's see, yeah, so for whichever positions we randomly sample, we'll just replace them with like some masking position. So let's go ahead and do that. So first we're going to do batch size by sequence length, basically, by embed dim is x.shape. And then what we're going to do is how many tokens do we want to keep after masking? So here, let's actually create a tensor. Let's do rand is torch.randn. Let's do a batch size of 2. We know it's going to be 196 by 768. That's the shape we'll be working with. So we'll do random masking on rand. And so the question is, how many tokens do we want to keep after masking? So num tokens to keep is going to be equal to int sequence length times 1 minus mask ratio. So if my masking ratio is 75%, like hide 75%, that means we want to keep 25% of the sequence length. So this should be 49. So let's double check that. We'll see it's 49. So that means of the 196 things coming in, 49 of them we want to keep, but the other 75% will get removed. And what we're going to do first is to generate some noise for sampling. So we're going to say noise is going to be torch.rand. So she'll generate values between 0 and 1 in the shape of batch size by sequence length. And we're going to make sure the device is equal to x dot, just make sure it's on the same device. And so all we've done is just created a noise matrix, right? Some value between 0 and 1. And what it really is for every single sample and for every single patch, you know, along the sequence length essentially, we've created some value between 0 and 1. And what we're going to do is this, our sorted index, so we're going to do sorted index is going to be torch.arg sort noise dim equals 1. So let's see what this looks like, sorted index. This essentially just creates indexes, right? 168, 128, 64, so on and so forth. And it's sorted in the order of greatest to least, right? So I believe it's greatest to least. Let me just double check. Least greatest. It doesn't really matter. Arg sort. Okay, so by default it's least to greatest. It doesn't really matter, so that's fine. So these are our sorted indexes. Now let me just make this clear by reducing the number here, like the sequence length. And actually, let's just do it for a batch size of 1 as well, just to keep this simple. Okay, so what we've done is we took indexes 0 through 9, and we picked however many, like we basically generated them, created some noise for them, and then sorted them. And so that's like, this was the smallest, and the next smallest, next smallest, next smallest. And basically what we're going to do is we're going to select our selected index. Our selected index is equal to sorted index. And ignoring that, we're going to do, so for every sample in the batch, we're going to do up to num tokens to keep. So we're going to now print out selected index. So all that's happened is, here's my random sort, and I'm keeping 75%. I have essentially 10 things here. So that'll end up, keeping these 2 things here. And so that's saying of these in random sort, these are the 2 indexes I'm actually going to keep. If I run it again, of course, it'll be different, but these are the 2 indexes I'll keep. So I'm going to toss the rest of this, and I'm going to keep these 2. The reason it's rounding down is because, of course, 10 is not divisible by Like we'd have 2.5 samples, so it just rounds down. So that's what the int here is doing. It's just rounding down, but that's fine. So imagine that all we did is for every single index, we generated some random number between 0 and 1. We sorted it from least to greatest, and then we just grabbed the first two things. And this is essentially going to random sample some positions, right? So every time we do it, we'll get some different set of positions that we are randomly grabbing to keep, and everything else disappears. But we also need something called the restore index. The restore index, so let's keep that. Our restore index IDX is going to be torch.argsort sorted index dim equals 1. And let's print out the restore index. So why are we sorting our sorted indexes? Because it's exactly this. If I say that, and actually let's also do this. Let's print out torch.arange sequence len, just so we have all three of them to compare against. So what we have is essentially we have 0, 1, 2, 3. These are our original indexes. And then what we've done is we randomly generated some number between 0 and 1 for all these indexes and then sorted it from least to greatest. But what I need to know is how can I restore this back? So the question is this. So index 0 is where along this vector? Well, that's going to be 0, 1, 2, 3, 4, 5, 6. So that's going to be 6. Where's index 1 along my sorted vector? That's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Where's index 2 along my sorted vector? 0, 1, 2, 2, 2. Where's index 3 along my sorted vector? 0, 0, so on and so forth. So that's all it is. The restore index tells me the position of each original token, like where is it in my new list. And the reason we need this is after the masking process, only the selected index, and so we grab the selected index, and the restore index lets me put the tokens back in their original position. So that's all. So basically, if I know where this is, I know exactly how to take this list of sorted stuff and just return them back into the original positions. The reason we need this is this, because when we do this, we need to make sure that we take our embeddings and put them back in the correct positions, exactly where they go. And so that's it. Relatively simple. It's basically just a double sort. We sort once to get a random sort and then random sample however many tokens we want to keep, but we sort the indexes again just so we know the placement back to where we need to put them. And that's it. All right. So going forward, we now can, let me make sure I keep this open. Here we go. So now what we need to do is also add an embedding dimension to our selected index. So if we look at our selected index, print selected index, it is this, which is fine. And if we look at the shape of it, of course, it's going to be batch size by sequence length. But what I want to do is grab these specific indexes from my original data rand. So let's make this even smaller so we can make it very easy to see. And let's make this even smaller. Let's make this 4. Let's print out rand, or print out x right at the top so we can see what's happening as we're going. Here we go. So we have a very simple thing here. And what I have is 1, 1, which is fine. That's the shape of it. Let's make it like this. So given this vector, what I want to do, and let's reduce the ratio a little bit. Let's say our ratio or mask ratio is going to be, let's say 0.5, just so we get some actual information here. So basically from this data, so sequence length by embedding dimension, I've randomly selected sample number 1 and sample number 4, 0, 1, 2, 3, 4. Yeah. So what I want is to grab this one and this one. And we can do that via indexing, or we can use the faster way of just using a gather. So how we can do that is this. To do gather, we need to first do selected index repeat is going to be equal to selected index unsqueeze -1. And then we're going to do dot repeat 1, 1 embed dim. And so now when we print out selected index repeat, it'll look like this. Basically, it's saying that I have 4, because our embedding dimension here is 4. I've created the one. What I want is the first one and the 0th one. But I've gone ahead and just I've gone ahead and repeated it for the embedding dimension. So I've selected 1 and 0 as the positions I want to grab. And now that I have those indexes, I need that index for each one of my embedding dim along the embedding dim, because that's what gather needs. And so now what I can do is very simply xMast is going to be torch.gather x dim equals 1. Why is it dim equals 1? Because these indexes here, 1, 0, whatever it may be, it refers to the first dimension, the sequence dimension. So dim equals 0, dim equals 1. That means my indexes can be anything between 0 and 4. In our case, we picked 1 and 0. And these indexes refer to that specific dimension in X. So that's why it's dim equals 1. And then our index is equal to selected index repeat. And that's it. So this unsqueeze setup is just to make sure gather is happy with this operation. And now that we have that, we can print xMast. And of course, we should keep printing out the selected index. And this should be pretty clear. So what I want is, from this data, I want basically position number 4 and position number 0. So that's position 0 is second. So there you go. These two match. And position number 4 is this one, which matches this one. So yeah, we have exactly position number 4, position number 0, and we kind of dropped all the other ones in between because we don't need them. And that's it, right? That's the entire gather setup. Nothing too challenging. Let's also go ahead and create a mask. So this indicates to us which indexes were selected to be kept or removed. So we're going to do mask is equal to torch.ones. And this basically says everything is being kept. So we're going to initialize as ones. Size and then sequence length. Device is x.device. And then what we're going to do is our mask is going to be num tokens to keep is equal to 0. So what we've done, so let's take a look at this. We've created a mask in this case, and we know that the first two things, so going back to our, let's keep these printed, print sorted index, print torch.arange 5 in this case. So these are the original indexes. These were my randomly sorted ones. And then of course I have my print selected index. So there we go. So that gives me my which two I actually selected. So from these indexes, I randomly sorted them. And then I go ahead and grab the first two. These are the two that I want. And right now I set it up as 0, 0, 1, 1, 1, just to match, because that's saying I want these two things, or I want these two things, and I don't want any of these. So these were the ones that we wanted. Everything else was masked. 1 means it was masked. And that's completely fine on its own. But of course, this doesn't really work out because we need this to say that I kept this position and everything else, 1, 3, or sorry, which ones did I want? I kept these two positions, 2 and 1, but I masked out 0, 3, and 4. So now we get to use that restore index. So if we do mask is equal to torch.gather, again, we're going to gather on the mask. Again, dim equals 1, because these indexes here refer to, the specific sequence length dimension. And the index is equal to restore index. So if we print out our mask now, it'll be pretty obvious. Basically, we said that we wanted to keep 0 and 3. That means 1, 2, and 4 were masked. So that means positions 1, 2, and 4 have 1s because these are the ones that were selected to be masked. And these are 0 because they were not masked. And that's it. So this gather again does exactly that, because in this mask, all we did is gather into the mask along that dimension with the specific restore indexes, which is why we have the restore index. And that's essentially it. So let me go ahead and delete you, delete you, delete you. And we're going to return our xMasked data, the mask itself, and then the restore index for later on. And that's it. Good. And I can delete you as well. Okay, good. Up next, we have our Patchify. So this is how do we take images and patch them up. Of course, we already did this right here. we have our patch embedding, which takes the images, cuts them up, and projects them, which is fine. But remember, in our loss function, we need to actually patchify our images so we know that my output patch, like this one here, I need to do the mean squared error between this patch and this patch. So I need to be able to take the original image and then cut it up into patches and then do the mean squared error. So we need to write a separate Patchify function because this patch embedding uses a learned patch embedding. So that's less helpful for us. We could have similarly written this Patchify function alone, and then instead of having a convolution here, we could have done the Patchify of the incoming image and then had a linear layer projecting it from the input channels to 768. That would also be completely valid. But typically in our vision transformers, we just use a single convolution here for efficiency purposes. But we need this Patchify method to do our loss function later. So to do this, we're going to def Patchify and pass in images. Our image size is, again, 224. Num channels is by default 3, and patch size is by default 16. And so to Patchify is very simple. Batch size is going to be images.shape 0, and num patches is going to be image size divided by the patch size. Of course, we're assuming it's divisible. And our patched data is going to be essentially, remember, our images are going to come in as batch by channels by height by width. And what we're going to do to this is each of this height and width dimension need to be split into basically num patches by patch size and num patches by patch size. So that's num patches by the patch size. So what we're going to do, again, this applies only to square images. We'd have to be a little bit smarter about it if we were doing non-square images, but this is fine for now. We want to make it batch by channel by num patches by our patch size, and then again by num patches by patch size. Basically taking the height and width dimension and splitting both of them from height and width to num patches by patch size. So to do that, very simple. It's just this right here. Batch size by num channels, by num patches by patch size, num patches by patch size. But then what we're going to do is, we don't really need it this way. We need to do some permutation. So what we're going to do, I'm going to fill in, so num patches is 14, patch size is 16, 14, 16. That will be our default. We need to group them together. So we're going to make it 14, and then we're going to make it batch by channel, which we know is 3. Actually, we'll move that to the end. So we're going to do batch by 14 by 14 by 16 by 16 by 3. So that's what we're going to do. That's the reshape we're going to do. And so to do that, we just need to do a permutation, which is pretty straightforward. Right? We're going to permute it. So it's going to be dimension 0, then 2, and then 4. And then we're going to do dimension 3, and then 5. And then we're going to have the channel dimension last. And now what we're going to do is flatten this 14 by 14 into the 196 patches that we expect it to be. And we're going to flatten the 16 by 16 by 3 into 16 times 3, which happens to be 768. And that's it. So this is the reshape operation that we need to do. So very lastly, we just have to do this. Basically batch size, we have our num patches squared, and then we're going to do num patches times patch size squared, because those are the dimensions that we just stuck together. And return patch, and that does our patchification. And so if we have random data, 1 by, or I guess batch size of 1 by 3 channels by 224 by 224, we can print out patchify rand.shape, and this should give us exactly what we want, 768. Good. Yeah, again, we're going to need this to essentially take our raw images and cut them up so we can compute our loss function, and that's it. Now that we have that, we can go ahead and keep making progress on our actual masked autoencoder. So at this point, this should be relatively straightforward. So we're going to do class VIT, MAE Encoder, and then module, def init, self, and we're going to pass in the config from above. So remember, again, we already defined our MAE config up here, and we have the encoders config here, we have the decoders config here, and we have some extra stuff for later, which we'll reference as we get there. Okay, so how we're going to do this is essentially we're going to store the config as a variable so we can access it. Config is config. And there's only a couple things that we're going to need. So first, the encoder is a thing that actually takes in the images. So we need to do our patch embedding. So I'll just paste things in as we go just to make it quick. So this is the patch embed module with its image size, patch size, in channels, and the encoders embedding dim, because that's going to be different from the decoders embedding dim. So that's our patch embedding. And then what we're going to do is our CLS token and sine cosine embeddings. Now, the CLS token, if you remember, is essentially going to be our classification token. Like when we do image classification, it's the CLS token that goes forward to do the image classification. We don't really need the CLS token for pre-training. We just include it. So basically it never gets updated. We don't do anything with it. We just include it here just so we can use it later on. We could also obviously just add it on in a different module, but it's easy just to have everything in one place. So we'll do that here. So we're going to do enc self.encoder CLS token is going to be nn.parameter torch.zeros. It's going to be 1 by config.encoder embed dim. So basically create a vector of length encoder embed dim. It's one time step, and we just have a 1 here to broadcast on the batch dimension. And I believe we've already imported all of this, so we're good. We similarly need our positional embedding. So self.encoder positional embed is going to be sine cosine embeddings. It's going to be num tokens is going to be equal to self.patch embed patch embed dot num patches. So remember, in our patch embedding right here, we defined a num patches, and the num patches tells me that this thing has 196 tokens, right? So that's how many positions we have. And so we need the same thing, patch patch bed dot num patches. So that's how many positions we have, but we also have +1, the extra CLS token. So we have basically 196 positions, but we have that 1 extra CLS token that we're going to concatenate on. So we have +1, and that's why it's there. After that, we have our embed dim is going to be equal to our config.encoder embed dim. That's the embedding dim for each of our embeddings for this. And then our requires grad is going to be equal to config.learnable positional encodings, I believe. So I believe I did this correct? Yeah. Okay, good. So yeah, up here in our configuration, I have a flag here. Do we want to learn them or not? True or false? It's up to you, whatever you want to set it to. So you can try it either way. Good. So now that we have that, we're going to go ahead and do our self.encoder blocks is going to be nn. So this is the actual, transformer stack essentially is going to be a block of our, and I don't want to type this out, so I will paste it. There we go. Basically, our encoder blocks will be the encoder blocks with the encoders configuration for all of our encoder depth. And again, the entirety of the encoders configuration is defined right here. So it's just using that information. And it's as simple as that, right? Now that we have that, that is our encoder block. We will also have self.encoder layer norm is going to be nn.layer norm config.encoder embed dim, and then EPS is 1, E minus 6 is the default, so that's fine. Okay, good. So that's it. Very simple. And so our forward method, forward self x mask ratio is 0.0 by default. Of course, it's going to be 75%, but we'll manually pass that in, so it's fine. Our output hidden states is going to be false by default because we don't really need that for our pre-training, but we'll see that in a second. So data, again, is going to come in here as batch size by channels, by height, by width is x.shape, right? That's the original data coming in. And then x is going to be self.patch embed x, so this is going to make it batch by 196 by 768. And then what we're going to do is add on our positional embedding. So x is equal to x plus self.encoder positional embedding. But we need to make sure that we only add it on for the non-CLS portion. So remember, the 0th position in our encoder, our positional embeddings, belongs to the CLS token. That's why we have a +1 right here. And then everything else after that belongs to our images, image patches. So right now, notice that we haven't concatenated on our CLS token yet because we haven't done the random sampling yet. So let's random sample some stuff, then add the CLS token, and then we'll be good to go. So all we're doing is, I know the 0th position is the positional embedding for the CLS token. Let's ignore that one for now. Just add for the first position, and we'll come back to that in a second. So if mask ratio greater than 0.0, so if there's any mask ratio, x mask and restore index is going to be equal to random masking x mask ratio is mask ratio. So this is the method we wrote earlier, right? Our random masking method will go ahead, take a mask ratio, and return the masked data, basically just the subset of the rows that we randomly sampled, the mask itself of which positions were selected to be masked, which positions were not selected to be masked, and the restore index, which lets us kind of revert back from where we started. And that's it. Otherwise, we're going to set mask to none and our restore index to none because, in that case, there is no mask and restore index, so we can ignore them else. Good. So now our CLS token, of course, is going to be self.encoder CLS token plus self.encoder encoder positional embedding. And this is where we're going to add on that extra CLS tokens positional embedding. So we're going to do that right here. So we index out of it, so we don't add it here. We just manually add it right here. And then our CLS token is going to be equal to CLS token dot expand batch size by -1, So remember, our CLS token was 1 by 1 by this. Both of these dimensions are fine, but this one dimension needs to be repeated to the batch size coming in. So this is us doing that repetition. And now we can do x is equal to torch.concatenate, and we're going to put the CLS token first and then x second along dim equals 1. And now let's go ahead and pass through the transformer block. So hidden states is going to be an empty list, and we're going to do for block in self.encoder blocks, x is going to be block x, and we're going to do if return or output hidden states. We're going to do hidden states dot append x, basically store each of the outputs of every single layer. That's it. And then one thing we're going to add, and this was I believe mentioned in the paper, so let's just verify where it is. Masking ratio, mask token, here, encoder. Where was it? Somewhere they mentioned that they add a layer normalization at the end of this architecture, but I do not remember where they mentioned that, but it's in here somewhere, so it's fine. So basically at the very end, we're going to do x is equal to self.encoder layer norm x, and we're going to do if output hidden states, return x, mask, restore index, and the hidden states. Otherwise, if we're not returning, then otherwise we just return our return x, mask, and the restore index. We don't really care about the hidden states right now. That will be later. But for now, this is all we need. Yeah, somewhere in the paper they mentioned this. I just can't remember exactly where. Good. So that's the encoder. Our decoder is going to be a lot of the same things. So class VIT decoder. Here, I'll paste the initial part in. Don't need that. Explain that anyway. So this decoder will only be used during training, during our pre-training. And so we're going to pass in the config, but we also need to tell it how many patches there are. Because remember, the decoder is going to get this, basically the subset of the patches. So like if there's 196, only 49 of them will be here. And so the decoder will only get the 49, and it needs to essentially do this re-indexing and stick in the mask tokens. So we just need to tell it how many things were there to begin with, and then based on that, it can do that. So that's why we also include the num patches right here. Self.config is our config. self.num patches is num patches and and so here's the first important step. Remember, our encoder and decoder have different sizes. So our encoder had an embedding dim of 768. Our decoder has an embedding dim of 512. So we need to make sure we project our embeddings from 768 to 512. Let's do that first. So the first step will essentially be self.encoder to decoder embedding proj is going to be nn.linear config.encoder embed dim to config.decoder embed dim. So this will go from 768 to 512. And then our self.mask token. So remember, our encoder had no, scroll down. Our encoder had no mask tokens. We just passed in the visible patches, and all the mask positions are left alone. The decoder will take the context vectors for those visible patches and place them in the correct positions, and then put in all the masked positions some learnable mask token, like we do for BERT. And so we just need to define what that mask token is right here. And this will look just like the CLS token. It's going to be nn.parameter, torch.zeros. I'm initializing zeros. We're going to write a init method later to actually properly initialize it. So this is fine for now. Torch zeros, 11, config and decoder embed dim. We, of course, once we do this, we need to again add, the decoder will have its own sine cosine embeddings across the whole sequence. So we need to make sure that we again initialize another set of sine cosine embeddings here. So that's going to be, and this is the same chunk of code from earlier. So actually I can paste all of this because all of this is now the same as earlier. So let's do that. So all of this is the same as earlier. We have our sine cosine embeddings, just like before. We have our decoder blocks, just like we had in our encoder. We had a stack of encoder blocks. Well, in the decoder, we have a stack of decoder blocks. We just have less of them. So if you remember, right, we have only 8 of them in the decoder, but we had 12 of them in the encoder. So there we go. And then we have our decoders layer normalization at the very end. So again, that's just like the paper. And so now let's go ahead and wrap up this forward method, def forward, self, x, restore index, and output hidden states is going to be false by default. X is going to be self.encoder to decoder embedding proj x. So take the data x, which is currently at 768 embedding dim, and project it to the 512 that we expect here. Also, x is going to be x, x is equal to x, 1 to end, blank. Technically, we don't really need the CLS token for anything. So that 0th position is the CLS token, and the CLS token is just extra. We just added it in so it's easy to access for another part that we'll write a little bit later, but we don't really care about the CLS token, so we just get rid of it and it's gone. We know our data is going to be in the shape of batch size by num selected index by embed dim is equal to x.shape. Remember, we may have had 196 patches in the original thing, but only 49 of them stayed. So x's shape here should be batch by 49 plus 1, which we ended up clipping off. So it's now just 49 again. And now we made this 512. And so that should be the shape of x. And so what we're going to do is first we're going to expand the mask token, repeating for the number of tokens that were masked. So our mask token is going to be equal to self.mask token dot repeat batch size, and then self.num patches minus num selected index, and then keep the last dimension the same. So all we did is we took our thing here. It was 1 by 1 by embed dim. We've made it batch size by basically 196 minus 49, the number of masked positions, and we don't need to change the embedding dim. That should not be repeated at all, so we just leave it as 1. And now what we're going to do is x token e x is equal to torch.cat x mask token dim equals 1. So this is essentially going to go ahead and take actual data x and concatenate on a bunch of mask tokens to it. And then what we're going to do is our restore index repeat is equal to restore index dot unsqueeze minus 1, add in the embed dim, and then repeat 1 1 embed dim. And then x is torch.gather x dim, or gather, not father, gather x dim equals 1, and index is equal to restore index repeat. So this should feel very familiar. Basically, in the utils, we did exactly this. In this setup, remember that we were indexing from basically this selected index repeat. The reason we repeated it was so that we could match our selected index to have the same dimensionality as our actual embeddings, right? The actual embeddings of x. And so this basically needed to match it so we could gather correctly. So that was step one, right? So we did this here because, of course, our restore index doesn't have an embedding dim. It's just going to be batch size by sequence length. We just repeat it to include the embedding dim just so gather is happy. So this is a property of gather. And then basically exactly what we did here, we created a mask where the masks, all the positions were set to 1, except for the positions that were kept. Those were set to 0. And then we use torch.gather mask dim equals 1, indexes restore index, in this case, to get the correct indexing of which indexes in the original, consecutive sequence 0, 1, 2, 3, which ones were selected to be masked, which ones were not selected to be masked. We're doing exactly the same thing, but now instead of applying the restore index to mask, because mask had the shape of batch by sequence length and restore index had the shape of batch by sequence length, we're applying restore index. We've repeated it to batch by sequence length by embed dim because x, the thing we're applying it to, is also batch by sequence length by embed dim. And we know the sequence length here is 196 because x had 49 things in it and mask token had 49 or 196 minus 49 things in it. So this basically is all the stuff. So this is back to batch by 196 by 768. And then all we've done is we know that the first 49 positions of this thing is the true data. Everything after that is the mask data, but we don't want it that way. We want it this way. We want everything in their correct position. So imagine that essentially we had all these true tokens, and then we just concatenated on a bunch of mask tokens at the end. But because we had the return index, we can put everything back in their correct places. So we know, for example, that position 0 and 1 were masked, and then position 2 is a true patch. So whatever this, whatever the output of this was. And then position 3, 4, and 5 were all masked. And then the one after that is a true, embedding. So we put the second one in that position. So on and so forth. We just repeat that down for all the dimensions, and that's essentially it. So yeah, it's just doing exactly what we did here, except we're doing the extra repetition to match the dimensions. And then it's the same gather that we did before, just now instead of applying it to a 2D mask, we're applying it to 3-dimensional embeddings, and that's it. But yeah, so same process. And then x is equal to x plus self.decoder positional embeddings. In this case, there's no clipping. We don't have to do anything because I know these positional embeddings have all the patches, and I don't have any CLS token or anything here. It's just directly add them and we're good to go. And then once we have that, we just do the same thing as before. Our hidden states is an empty list for a block in self.decoder. And actually, I'll just paste this because it is the same thing. Just to go a little bit faster. There we go. So yeah, go ahead and pass through all the blocks. We don't really care about the hidden states of the decoder at all, but it's there just in case for some reason. This is if you want to do the linear probing, for example, and kind of see what kind of representations the different layers are learning. Well, this is where you would do that. So you could take a look at these hidden states. And we have that final layer norm, of course, and we're done. That's essentially the entire masked autoencoder model. So you see, it's not very hard at all, actually. So on to the next thing, class MAE For Pretraining, nn.module, def init, self config mask ratio, which I'll set to default of 0.75 because this is our one for pre-training, and self.config is our config, self.mask ratio is the mask ratio, and then we have our self.encoder, which is going to be MAE Encoder with the config, and we have the self.decoder, which is going to be, again, the MAE Decoder config but the num patches is going to be our self.encoder. Inside the encoder, we're going to look at the patch embed. Inside the embed, we'll have the num patches. So how many patches do we expect again? Because again, we need to compute this, right? I know I have 49 true tokens, but how many masks do I need? So I can do the, the resorting essentially. That's our decoder. And then we have our self.embed to image. This is important. This is going to be nn.linear from self.config.decoder embed dim to, remember, we need to do the mean squared error. So every single patch of the image, so let's look here. Basically what we're doing is predicting something about this patch. Well, how many pixels are in this patch? We know that right now, this specific patch is represented by a vector of length 512 because the embedding dim of the decoder is, well, 512. But I know that each patch should represent a 16 by 16 chunk times 3 channels, right? That's the number of pixel values in every single one of the patches. So we want to make sure our linear layer projects to exactly this value. So it's going to be self.config.inChannels times self.config.patch size squared. And so basically this is a projection to the pixel space. Okay. And we're going to write our forward method first. Forward self x return mask is false. Okay. And what we're going to then do is our encoded mask restore index. Encoded mask restore index is going to be self.encoder x, and then our mask ratio is equal to, let's make sure it's explicit, self.mask ratio. There we go. So this is me taking data, passing it through the encoder, and I know the encoder is going to return x, the mask, and the restore index. So there we go. And actually, let's go ahead and actually test this out now, because we're at this stage, so it's easy to just pass things in and check for shapes. So our model is equal to VIT MAE for pretraining. Okay, rand is the same shape, and we're going to do model rand. So if we look at our encoded shape, print encoded.shape, we should see only a subset of our data. So we have, what are we doing here? Encoded.shape, mask ratio is set to 0.75. Let's see here. So in the encoded, let's see where I've gone wrong. Here we go. Let's print x.shape right here. Okay, let's print it right before as well. Oh, am I missing something? Let's see here. VIT MAE for pretraining. We have our self.encoder. Oh, whoopsie daisy. I'm running the utils file. My bad. We should be running this file. There we go. All right, good. So I'm missing a thing, but that's better. So let's delete these extra prints real quick. Get rid of that. Get rid of that. And what we're going to do is pass in the config. So the config, of course, is going to be the VIT, what did I call it? Let me double check. I called it, just MAE config. Okay, there we go. So we'll use the default config for now. Okay, and we'll go ahead, pass in the config. Oh, and we can leave model rand. Let's see if that works. Okay, I'm missing a super somewhere. Super.init. Sure, I'm missing it in a couple places. Let's see. Nope, got it there. Missing it here. And I think that's it. So let's see. Okay, almost there. So encoded, this should be mask, comma, restore index. My bad. There we go. Okay, good. So now, if we take a look at the encoded, print the encoded dot shape, we should see we only have 49, or I guess 50 positions with the CLS token right there. So there we go. That's the subset that we're passing through. In the same way, we have our mask, right? So of those 50, of the original 196 positions, which 50 does this specific sample represent? And so we can see these are the specific positions that were sampled, the 0 positions, and the 1 positions are ones that were masked out. And there we go. Okay, so now that we've passed it to the encoder, we need to also do our decoded. It's going to be self.decoder encoded. And we're going to also pass in the restore index, right? Because we need that. So now we can print decoded. And let's print out the shape of the decoded. That's going to give us back to 1 to 196 by 512. Now what we're going to do is for every single patch, so there's 196 patches, every single one of them, we're going to project them back to the pixel space, which we know has this many pixels in it. So that's pretty easy. We can do logits. Logits is equal to self.embed to image decoded dot shape. So now we have 196 by 768. And now what we're going to do is essentially our original data, right? Here's the key idea. X, so let's print out X dot shape. X is batched by channels by height by width. And here I have my 196 patches, each patch consisting of 768 pixel values, right? And so all I need to do is patchify this, my original data, and then do the mean squared error between the two, right? So let's take the original data, the original untouched X, so it has the true pixel values in it, patchify it. So let's do that first. Let's do patched. Two options, right? We could either patchify this or we could unpatchify this. It doesn't matter. So we could either take this and return it back to this shape, or we can take this and put it in this shape. It doesn't really matter what order or which direction you go in. You can pick either one. But we wrote the patchify already, so let's use it. So patch target is equal to patchify X. So if we print patched target dot shape, it should match the shape of the logits. And there we go. So these are the same. This one contains the true pixel values. This one contains predicted pixel values. And so now all we have to do is very simply a mean squared error. So our loss is going to be our logits minus the patch target squared. Now what we're going to do is first, if we print out the loss.shape, this should have the same shape as my original, right? So because it's just the mean squared error between per element values. What we're going to do now is we're going to do loss is equal to loss.mean dim equals -1. Let's go ahead and just take the average pixel value error per patch. So for every single patch, 196 of them, we have 768 pixels. Let's do the average over those pixels per patch. And the reason we did this is, remember, and they say this very clearly in the paper as well, when we compute our mean squared error loss, which they describe right over here, reconstruction target, we compute loss only on masked patches. So we only want to compute the loss on the things that were masked. The problem is right now, our loss is for all 196 patches. So what we're going to do is zero out the unmasked patches and then just average up the rest of them. So we're going to do loss is equal to loss times mask dot sum divided by mask.sum. So mask.sum tells me, remember, mask is 0 for the things that were kept, 1 for the things that were, 1 for the things that were masked, and then 0 for the things that were kept. So if I add them up, that gives me how many elements did we keep, and then we're just essentially multiplying the loss by the mask to zero out those elements, add them together, and then we just do a simple average, right? So we're just doing an average across only the unmasked portions. And that's it. Okay, we're only doing the average across the masked portions, right? Only for the masked portions. So yes, because 1 indicates mask, that means the sum of the things that were 1 is how many elements were selected to be masked. Of the 196, how many things were selected to be masked? On the things that were selected to be masked, divide that by, again, the sum of only the elements that were selected to be masked for those specific patches. That's it. So if not, return mask. We're going to return encoded, decoded, logits, loss. Else, return encoded, decoded, logits, loss, mask. So yeah, if we don't need to see the mask, then we don't need to return it. If we want to see it, then we'll see it later. It's useful for visualization, so we'll see that later on. So that's fine. Good. So now let's go ahead and write our baseline masked autoencoder. So technically we have everything we need now. For pre-training purposes, we are good to go. But if we want to fine-tune the model, we have a little bit of more work to do. So let's go ahead and write the two base modules. Again, we're only going to do for classification today. And then next time we will do segmentation because that's a little bit more work and I don't want to put it all in one video. So class VIT MAE for downstream tasks and then dot module. So this is going to be kind of a generic backbone. And what we're going to do is essentially this self. We're going to do super.init. And the idea is very simple. Basically, we're going to write a method called def load backbone. Okay, it's going to take a self and a config. So in our method, in our configuration up here, what we included was this extra stuff here. Whether or not, if we're using a pre-trained backbone, then are we using our own pre-trained backbone? Are we using a Hugging Face pre-trained backbone? Or are we just going to start from random? Like, don't start with any backbone. And that's all fine. And by default, we're going to say use a our own pre-trained one. And then if we're passing our own pre-trained one, then what's the path to our pre-trained weights, like the save tensor file? Or if we want to use a Hugging Face one, what's the name of the Hugging Face model that we want to use? And they call it this. So that's the base MAE model. And so that's it. Very simple. We just want to make sure we can load our backbones dynamically. So how we're going to do this is very simple. We're going to do if config.pretrained backbone is going to be pre-trained Hugging Face. So if we want to use a Hugging Face backbone, that's fine. Our backbone is going to be VIT MAE model. So we imported this at the very top right here. And so that's, again, from transformers. So we're going to use that. And we're going to do it .from pre-trained. And we're going to grab it from the config.hf model name. And that goes ahead and loads our actual backbone. And we're going to set backbone.config.mask ratio equals 0.0. There's no reason to do any kind of masking when we're fine tuning, so we manually set it to 0 and we're done. Otherwise, if our backbone is equal to VIT MAE Encoder, right? Basically the class that we wrote, that'll be the backbone. And we'll load it with the same, the config file. There we go. And what we're going to do now is if, here, I'll copy this piece here, just so I don't have to type it all out, just some exception handling. So if we want a pre-trained backbone, then we have to do two things. So if the path to pre-trained backbone is none, we can go ahead and just raise an exception because we can't do anything if we don't pass it. Otherwise, if it's not none, then go ahead and just do if not os.file. If if the path we provide doesn't exist, then we also throw an error. Otherwise, we're good to go and we can load correctly. So yeah, so it's just some path sanity checks. And so once we've done that, what we do is very simple. Our state dictionary is going to be load file. So this is the safe tensors load file to load a state dict. Config.path to pre-trained weights. Just go ahead and load those. Now, one thing that's going to happen is these pre-trained weights are going to contain a encoder dot stuff and also the decoder dot stuff because the model we're saving is the VIT MAE for pre-training. So it's going to have weights for the encoder and the decoder and also this stuff here. All we need is the encoder stuff. So let's just go ahead and filter out all the keys that we don't care about. So we're going to do backbone keys is going to be an empty dictionary. We're going to do for key in state_dict.keys for every single one of them. Just do a sanity check. If decoder in key, so if the word decoder is in the key, which it shouldn't be, or embed to image in key, if either of these things are in there, then we're just going to continue. We don't want to do anything with them. Otherwise, we're going to do our new key is going to be key.replace. We're going to replace the encoder dot with nothing. So we just remove that part from the name. If key dot starts with encoder dot. So just do a sanity check, because of course we don't really need the encoder dot anymore, as we're loading directly into the encoder. So this extra name, this encoder dot that comes from here, is no longer needed in that wait name if it's there. Otherwise it's just key. And then we can do backbone keys with the new key is equal to state_dict with the old key. So just go ahead and create a new dictionary of weights, and then very simply we can just load weights. So we're going to do backbone dot load state_dict our backbone keys. Okay, and that's it. So that will let us go ahead and we can now return the backbone. So this will just dynamically load. Are we using a Hugging Face backbone? Are we using our own backbone? If we're using our own backbone, then which one, how do we want to load it? Notice that if we don't do anything, then it'll just load random. So, if we don't load anything, then it'll just start with random initialization, and that's it. Okay. Next, we need our VIT for image. So this will be the MAE for image classification specifically. So I'll paste the initial part in. So this is just a wrapper, right, on the downstream task method we just wrote. And we're going to load the config, and the encoder will just be self.load, because we just wrote that method, load backbone, and we pass in the config, and it'll just go ahead and load the backbone for us. Now that we have that, we can do self.hf backbone. It's going to be false by default, but if config.pretrained backbone is pre-trained Hugging Face, then we're going to do self.hf backbone is true. The reason we're doing this is the way we pass data into our Hugging Face model is just a little bit different from how we pass into our own model, of course, so we need to keep in mind. And then self.head is going to be nn.linear layer from self.encoder.config.hidden size if self.hf backbone. Else, it's just going to be config.encoder embed dim. So this is, if we're using the Hugging Face backbone, this is where we get the hidden size of basically the embedding dim of the encoder from the Hugging Face backbone. And if we're using our own, then this is where we get it. And so it's just, a little bit different. And then we want to map it, of course, to config.num classes. And that's it, right? So this is just our prediction head, classification head, like normal. What we're going to do now is our forward method, self_x. If self.hugging face backbone, then we're going to do our output. It's going to be self.encoder x. And we're going to grab specifically the last hidden state. That's just how we grab it for the Hugging Face stuff. Otherwise, our output and then the other stuff that we don't really care about is going to be self.encoder x. That's how we grab it for our model. And the CLS token, remember, is going to be the output, and it's going to be just that first index, right? The 0th index. And the logits is going to be self.head CLS token. And then we can return logits, and that's our standard vision transformer setup. And that's it, right? Very, very, very simple. Of course, we still have to write our segmentation, but like I said, we're not going to do that today. So we're going to keep that for later. I am going to go ahead and copy our weight. So this is actually exactly like the vision transformer. It's a standard weight initialization. We do normalization initialization of all of our CLS token, mass token, all the projections, the weights, so on and so forth. So it's just standard initialization. And we want to make sure in our for pre-training up here, right here, we're going to do self.apply init weights. So we make sure we properly initialize the weights. And that's kind of it, right? So that's all there is. We don't need to worry about anything else here for today. So let's go ahead and now write the training script, which is very, very, very easy. It's very easy because we've already written the, we already have the loss calculation inside the model alone, right? So returning the loss right here. So yeah, it's very easy. So let's just go ahead and write the pre-training script. So we're going to open new file, pretrain MAE.py. I'm going to copy all the basic stuff. So I have a huge, yeah, I'll just copy up to everything that is easy, and then we can write the training loop together. Yeah. Wow, a lot of stuff. Okay. Yeah, so I'll just paste all this in. There's really nothing here, so I'll just quickly walk through it because standard, it's just like every other training loop I've ever written. So we have our, again, I'm using accelerate for distributed training because that's what I like. So you can change it if you want to something else. And we have here essentially that VIT, MAE for pre-training that we're going to be training. I have my argument parser. These arguments are pretty straightforward. The experiment name, which will point to some working directory that I want to save my checkpoints in, weights and biases, run name, the path to the data, like the ImageNet folder, and then the working directory that I want to store stuff in, so that's fine. How many epochs do we want to train for? I trained for 800, but the paper trained for 1600, so of course the results were a little bit better. They basically did 40 warm-up epochs. Every 10 epochs we're going to save something. I did a per GPU batch size of 256, which I think is pretty close to what they did. Let me double check here. Batch size. Oh no, not even close. Yeah, they did absolutely massive batch sizes. So we can see for pre-training, they had batch sizes of 1024. So I don't think I did 1024. I think I was, actually I might have been at 1024. I don't know. I trained this on a A100, like a 4x node, and I think the batch size was 256. So I actually might have, I think I actually did that, so that's fine. Okay. Okay, we have a GPU batch size, gradient accumulation, base learning rate, weight decay, all that stuff. We have our standard like data loader stuff. We have all the model configuration, which we can control through the config file or through the arg parse, but of course it's all in the config file, so it's fine. And then whether or not we want to log weights and biases, and if we need to resume from a checkpoint, that's fine. And so we go ahead, we instantiate a path to our experiment, which will be in the working directory / experiment name, whatever we set it to. We initialize our accelerator. We go ahead, and if we are logging with weights and biases, here's all of our experiments information. Go ahead and initialize the tracker like that. We have the masked AutoEncoders config, just loading stuff from the arg parser. So standard. We have our vision transformer VIT-MAE for pre-training. So there's our model itself. We can count the number of parameters in the model. Remember in this paper, they found again that the doing overly complicated image transformations didn't seem to help, surprisingly. So if we go back right over here to one of their ablation tables, they find that the best results came from just cropping and random size. So we do the same thing. So we have random resize crops, horizontal flipping, converting to tensor, and then standard ImageNet normalization for the, scrolled up. Standard ImageNet normalization for training. For the testing data set, same idea, but we're just going to do resize to tensor normalize and nothing else. To load the data set, we're going to be training on ImageNet, which has a train and validation folder, each folder having its subfolders. So again, if we go to data and then where is it? Here, ImageNet, there's a validation folder, and then the validation folder has all our subfolders with actual images in it. So in this situation, we don't really need to do anything. We just go ahead and the dataset's image folder just does it for us. So we're done. We have our data loader, but of course, if we're doing gradient accumulation, then we're going to take our batch size and split it up. And so the mini batch size will be the per GPU batch size divided by the gradient accumulation steps. Go ahead, load our 2 data loaders for training and testing. And then here's our effective learning rate. So this is using linear. So we have our base learning rate times the GPU batch size times the num processes divided by 256. This is the effective learning rate, just using a learning rate like, scheduler, that sort of stuff. So this is our batch adjusted max learning rate, essentially. This is also in our vision transformer, where essentially based on the batch size, we scale our learning rate up or down. Bigger the batch size, the more confident we are about our gradients. And so the more confident we are about taking bigger steps, and so batch size kind of will scale up our learning rate a little bit. So batch adjusted max learning rate. After that, we have our optimizer. This is pretty standard. There's a bunch of like extra stuff in here that we don't care about. Essentially, we're looping through, and we essentially don't want to do weight decay on our bias terms or batch normalization terms or weight normalization terms. So we can go ahead and just turn those off. So that's all this is doing. If we don't care about any of that, then we just load our model and we're done. The betas here, just 0.95. I think that's actually wrong. I should have used the, I think they did not 0.95. I think they did 0.999. Let's double check here. Let's see, right here. So yeah, they actually did, oh, actually it's right here. So I followed this one. So yeah, 0.999. Oh, I see, this is the fine tuning one. Yeah, it was not even close. They used a batch size of 4096 for this model. So yes, that is not what I did. So either way, they use this, they use 0.9, 0.95. So I set it to the same thing, 0.9, 0.95. We have, whether or not we want to use fused atom or not, we might as well. And we have our weight decay, of course, which I also set to the default of 0.05. We have how many steps we want to train for. We have our cosine scheduler. We have to prepare everything for the accelerator. We register our scheduler for checkpointing. And then, of course, I'll also paste this last piece in. If we are resuming from training, we need to load our weights. So if we're resuming, go ahead, load the last checkpoint, go ahead and load it to accelerator, and then our starting checkpoint will be this. And so how I'll be saving stuff is going to be basically checkpoint underscore epoch, right? That's my naming strategy. So the starting checkpoint, right, it will be here. Okay, so now we're going to do for epoch in range starting checkpoint to args.epochs, however many we want to do, accelerator.print f training epoch, so print it out, and we're going to do our train loss as an empty list, test loss is an empty list, and accumulated loss is going to be 0. And let's go ahead and make a quick progress bar. Of course, our train loader is scaled up by gradient accumulation steps, so we need to divide by that to get the true number of steps, because if we have truly 100 steps, but we split each step into 2 steps, then length of train loader would be 200, so we need to just scale it back, and we'll manually step through them. And this is pretty damn easy, right? So we're going to do model.train. For images, it's going to return labels too, but we don't really care about those, right? Because this is unsupervised. In train loader, we're going to do our images is equal to images.to accelerator.device to device, and then we're going to do with accelerator.accumulate, so we can use our context manager to easily do the accumulation here. And we can then do our encoded, decoded, logits, and loss is going to be equal to our model, and we just pass in the images, right? That's exactly what our pre-training model will return. Our accumulated loss, we'll do plus equals loss divided by args dot gradient accumulation steps, just scale it down. So this is mostly for logging. And then we're going to do accelerator dot backward loss. And then we're going to do if accelerator dot sync gradient. So every time every time we synchronize gradients, which will be every gradient accumulation step. So if this is set to 10, every 10 steps we're going to synchronize gradients. Otherwise, it's it's an unnecessary process. Otherwise, we can go ahead and do our clip grad norm, accelerator dot clip grad norm model dot parameters args dot max grad norm. We're going to do optimizer dot step optimizer dot 0 grad set to none is true, and then we can do scheduler dot step, and that is one completion. And then we can do if accelerator again dot sync gradients. Once we're done, means we've completed one full accumulation. Let's go ahead and just go ahead and do our logging. So we're going to do our loss gathered is equal to accelerator.gather for metrics accumulated loss. Just go ahead and grab those. So this will return, if we're training on 4 GPUs, basically a tensor with 4 values in it, 1 per GPU. And then we can do train loss.append torch.mean loss gathered dot item. Right? Just average it, grab the item, and we're done. Reset the accumulated loss to 0, and then our progress bar gets an update, because that means we've completed one full accumulation. Our evaluation loop is identical, so I can just paste it in, right? Evaluate, loop through, torch.nograd, same thing, store, average, print, log to weights and biases, checkpoint every now and then, end training, and we're done. So you can see, very, 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 very easy training loop, right? Really not anything going on here. Oh, there we go. Yeah, really nothing going on here. That's all that challenging. So now that we have all of that, let's just give this a quick try. To do this, I need my, here we go. I'm going to new file, pretrain.sh. Here we go. We don't have the resume and I won't log. Yeah, and I will do MAE pretraining. This will be, let me see here. What was the, yeah, we wanted that, so that's fine. Yeah. Okay, I'm going to call this test, whatever. And I need to make another folder in here called new folder, work, dir. There we go. And so let's see. So these are all our standard defaults. I believe, yeah, the data is saved there, so I think it'll be good. So let's try this. Accelerate launch pretrain MAE.py. So this should work, but we'll also find a bug if there's a bug. So here we go. Bug time. Did you mean VIT MAE for pretraining? Can't import this. Okay, let's see. I probably spelled it wrong. VIT MAE for pretraining. There we go. Misspelling. Okay, let's see what else. Okay, we're getting closer. Following arguments are required. Experiment name, path to data, working directory. Did I miss something? Experiment name, weights and biases, run name, path to data, working directory. Oh, of course. I need to run it with the bash script, right? So I need to do bash pretrain dot. There we go. Okay, so that'll actually run it with our function arguments, or our argparse arguments. And so yeah, we see there's 111 million parameters. We know a base vision transformer has about 86, and so the other 30 or 40-ish is the decoder. So it's a lightweight decoder. So there we go. That's why. And so we'll give this a second. We'll see if it actually starts triggering. We see the learning rate. We set it to 1.5e -4, but we scale it up or down based on the actual, we scale it up or down based on the actual batch size. So larger batch sizes, we can get away with larger gradients. Smaller batch sizes, we can get away with smaller gradients, so on and so forth. And so yeah, we can see training has been triggered. We can double check here, NB top. We can see both GPUs are indeed being used, so that's good to see. And that's it, right? So essentially this works out to being about like, I don't know, locally it's about 14-minute, 15-minute epochs. On the cluster, they're like 6-minute epochs, so it's very quick. But yeah, so we'll let this, of course, I'm not going to make y'all watch a training loop, because who wants to do that? So let's briefly look at results and fine-tuning, because like I said, the fine-tuning of this model is not that interesting because it's copy-pasted. So let's just go through the remaining little results, chunks of code, things like that. So first, for the fine-tuning of the MAE classification, this code, like I said, is directly copy-pasted from the original vision transformer implementation, so you can go and watch that video if you want to understand what's going on here. But there, if you just look at this, there's nothing interesting going on. It's the same training loop as before. It's just the only difference now is, of course, we're going to be using the cross entropy loss. And also, like we talked about, when we train vision transformers, they require a lot of like downstream or a lot of data augmentation. So I also went ahead and included some of that stuff in here somewhere. Let me remind myself, where would that be? Let's go back. We grabbed it from datasets, utils. Let me double check here. Where did I put it? It is in, oh, I guess it's still in utils. Okay, so here we go. So yeah, we implemented this stuff. Oh, okay, I guess I'm missing it. I need to add it back in. Either way, so yeah, basically in our vision transformer, let's just go right here, vision transformer, we had, here we go, I think this is the util. So we implemented all of these like transformation stuff, cut mix and whatnot. I just included it here as well, so it's not that big of a deal. So yeah, just keep that in mind. But the fine tuning is, again, just like fine tuning a standard vision transformer. It's not really interesting. So that's why we're not going to implement it directly. What we will implement later is the upper net, because that actually is interesting and requires a meaningful amount of work. So we haven't done any of that yet. Of course, looking at this, so let's look at a little bit of results. First, so after pre-training the MAE, we can see the pre-training results right here. Give it a second, and there we go. So we can see our loss kind of steadily decreases over time. There's no evidence that this is going to stop decreasing. This probably would continue to do better if I scaled it over, 1600 epochs like they did. So the reason you start to see it really decay off at the end is because also notice that our learning rate has also really decayed off here at the end. So that those two patterns kind of match. We could have easily trained this longer and gotten the actual final result. But our loss drops to essentially about a 0.24-ish range, which is good to see. So it starts at like 1 point something and drops to 0.24. Good. So that is our loss plots. So we can do that training for 800 epochs. And then the other interesting thing is, now that we've actually pre-trained our master autoencoder, what do these reconstructions look like? Let's go back. And we can see it looks like this. So here's a picture of my cat. I've gone ahead, we've removed 75% of the pixels, and then all I've done is I plotted the reconstructions back. This is the reconstruction of every patch, but then of course, a lot of these patches are masked. So then I also filled in, so basically the patches that were real earlier are still there. And then the black portions here are the ones that I plotted. So the reconstruction masks are there, and then the original input mask, like the unmasked stuff, is the original pixels. And so we can see this is actually pretty good, given that like this is not an image the model has ever seen. It's not a part of the ImageNet dataset. This is my picture of my cat. But this seems to be a relatively good reconstruction of what we started with. And just to show some more examples, right? There are plenty of these examples in the paper, in the original paper. You see that they get very similar results. And so you can see that they kind of get similar results. Of course, it'd be interesting to take a look at some of this. So let's maybe do that. CD masked autoencoder. We'll look at my actual implementation. I have a Jupyter notebook that will produce these masks for us. So we can briefly take a look at that because it's not that interesting, just easy. So we go ahead, we load our model, the pre-training model, we load it, and then this is the sample, this is our standard transformation. So there we go. And then we just had to write a couple of easy methods. The first one was the Patchify went from this to this. Unpatchify just does exactly the opposite. So there you go. That's our unpatchify method. It's just the opposite of the patchify method. This is mostly for visualization, so don't worry about it. It's mostly about getting these black portions in the overall image. So it just does that. And then this is just to convert from a NumPy array to like an image so we can actually plot it, right? So we go ahead and inference it with a mask, and then we go ahead and just make the plot, and it looks like this. So let me actually run it from the top, and we can explore a couple of small details. So first, when we run this, give it a second. It's not going to be rand. I bet I just renamed it and forgot to change it again. Where are we looking? Where did it say? Oh, it's in the torch.nograd. So that'll be right here. Yes. So this is going to go. This is going to be image. There we go. So that's what we had, right? So pretty good of a reconstruction. But this is with 75% of it removed. What happens if we reduce the percentage? So when we loaded our model right here, let's say we reduce this to 0.3%. So only 30% of the image will be masked. How well can it do then? We see it gets better. Of course it gets better because there's more information for it to predict the missing pieces on. If we pick a higher percentage, let's pick 0.9, we would expect the performance would be worse, right? So these are not really, I mean, there's so little of the image here that it's honestly impossible for the model to predict what's there and what's not there because it's never been trained at such a high rate. We can try slightly higher, maybe 80%. And this is, it's fine, it's close, but, still not as good. So this is our essentially plots, right? We can take a look and see how the model does its reconstructions, like what is it actually predicting on the other end, and this is what it is. So, okay, and I believe that is it for this part. So then going on, of course, there's 2 downstream tasks that we do. The first one is the classification, so we can take a look and see. So like I said, I just copy pasted my original VID training script and just used it directly. And these are the results. So, and this is the important part, the vision transformer trained for 100 epochs. So this is a standard vision transformer with nothing else. Trained for 100 epochs gave about 62% top 1 score. And then trained for 300 epochs gave almost 80. It was like 79% top 1 score. But my masked AutoEncoder, which has already been pre-trained for 800 epochs, gets an 81% top 1 score right off the bat at 100 epochs. So we can see that we're already beating the vision transformer in 100 epochs, even though the vision transformer was trained in 300, which is kind of cool to see. I never actually trained for the full 300 epochs for the MAE. I didn't want to wait that long. But the original MAE repo reports, again, an 83.6% accuracy, but that's probably a mix of they trained for longer when they did the fine-tuning, and of course they also trained double the length when they pre-trained it for 1600 epochs rather than for 800 like I did. Our next step is going to be our segmentation model. So just to give a little bit of context, I actually used this architecture a while back. So in this paper, which we put on archive a while back, we were interested in doing self-supervised DEM modeling. DEM modeling is like digital elevation information. Basically, it's like every pixel is like the elevation or whatever. And we wanted to predict things like the roads and whatever else it may be from these images. But of course, we wanted to see if we could kind of pre-train on these DEM images and then fine-tune it to do our segmentation task. And it actually worked out. So we basically pre-trained our masked AutoEncoder on all of our DEM images, and then we fine-tuned them with the upper net head to do our segmentation task. And so this is what we'll be focusing on next time. It's a little bit more interesting, I think. And so to write the segmentation task, it's relatively straightforward, but we'll get results like this, right? So we're gonna write a standard segmentation model on the 8020K dataset and just see how it goes. So that's it for this video. I hope it was helpful. I think this is one of the coolest architectures ever. Like I mentioned, people are using at least the ideas from masked AutoEncoder all over the place. They're using it in the audio space, like they're using it for training masked AutoEncoders on spectrograms. That's that MAE masked AutoEncoders that listens paper. And of course, masked AutoEncoders have started to morph into these kind of latent prediction models, the JEPA architectures, like the JEPA class of architectures. So this is kind of a stepping stone to get to JEPA because that's the model I really want to implement for y'all. So I'm going to call it here, and I will see y'all in the next one.